Hello everyone, my name is Ting Yuan, and it's my pleasure to present our work at LMPL on exploring whether language models can assist in core graph construction. This work was carried out with my colleagues at Huawei, and our goal is to investigate the potential of LMs in one of the long-standing challenges in program analysis. Large language models have shown remarkable progress in coding tests. For example, GitHub Copilot can generate nearly half of a developer's code, and Human Evil benchmark reach pass at Wang of 94%. But these tests remain at the function level and rarely capture caller-callee relationships across repositories. Yet, core graph are essential for software engineering tasks such as optimization, bug detection, and security analysis. Unfortunately, by race theorem, core graph construction is an undecidable problem. Static analysis tools cannot perfectly solve it either. So our central question is, can language models help with real-world core graph construction? To answer this, we built SageBench, the first benchmark designed to evaluate LM's understanding of core graphs. It contains 104 cases manually carried from 7 large-scale C and C++ open source projects. Each case includes an indirect call site, the related code snippets, and the ground truth callee functions. Cases cover macros, complex data structures, and dynamic linking, reflecting real-world program complexity. Our dataset comes from several well-known system-level projects: GCC, FFmpg, Redis, ZFS, Cure, OpenSSH, and WRK. Together, these projects contain almost 9 million lines of code and about 18,000 indirect calls. From this large code base, we carefully distilled 104 challenger cases that make up SageBench. For example, this is a classical dynamic linking pattern. The code first constructs a symbol name by concatenating a prefix with the string OMX in it. Then it calls DLSym to resolve that symbol from a shared library. The pointer is stored, and later on, another function invokes it indirectly. So the real callee here is OMX init with a prefix. Now, why this is difficult for traditional static analysis? There are two main reasons. First, because the callee is covered by only at runtime, not visible in the code. Second, because the target depends on string concatenation, which requires complex symbolic reasoning. Large language models can help here. They are good at understanding naming patterns and local context, so they can infer that the result is very likely OMX init and propagate that to the indirect call site. The takeaway is that even though dynamic resolution is hard-bounded boundary for static rules, LMs can often succeed when the code provides clear naming and simple string assembly. Our experiments for SageBench were conducted on 2 NVIDIA V100 GPUs. We evaluated 4 widely used open source code language models: CodeLlama 7b, CodeLlama 13b, DeepSeek 6 LMPL'25.7b and DeepSeek 7b version 1.5. For evaluation, we used accuracy, precision, recall, and F1 score, treating this task as a multi-label classification problem. The task itself is quite straightforward. The input is an indirect call site together with its related code snippets. The output is the actual function or functions that the pointer may invoke. We tested 3 property strategies. First, zero shot. Second, improved zero shot, which is more structured and better formatted. And third, few shot, where we provide examples inside the prompt. The results are quite encouraging. All models achieved over 50% accuracy, even in the basic zero-shot setting. When we used improved prompts, the accuracy went up by about 2 to 11%. In particular, code Llama 13b with improved zero-shot property reached 67.7% accuracy, with a F1 score of 18.4, and the best performance came from DeepSeek 6.7b in the few shot setting, reaching 69.7% accuracy and a F1 score of 83.6. This results suggest that large language models already show substantial potential for assisting in call graph construction. From our experiments, we draw 4 key findings. First, LLMs can make use of information that static tools ignore, such as comments, naming conversions, or even strings set for function names. Second, they can follow data flows, tracing function pointers across both simple and complex paths. Third, irrelevant information can haunt performance. And the fourth, ending unrelated code or misleading variable names can confuse the model. Most importantly, this points to a broader shift. Program analysis in the future will not be limited to syntax and semantics alone. It can also draw on textual signals, names, comments, documents, even the way a repository is organized. This opens the door to a new kind of hybrid program analysis that combines formal methods with the soft knowledge embedded in real software projects. Let me briefly share what we observed from the case study across projects like Redis, ZFS, FF, MPG, WRK, and Cure. Large language models were able to handle a variety of challenging patterns, from blank box library calls and develop comments to dynamically built function names and complex macros. These examples suggest that LMs are not just simple pattern matchers. They actually show reasoning abilities and reasonable program analysis. All of these cases are open source, and the full benchmark is available on GitHub for the community to explore. To conclude, we present CGBench, the first benchmark for testing LM's understanding of C and C++ core graphs. Results shows that LMs can already perform well on this challenging task, in some cases outperforming static rules. Future work will expand CGBench with more languages, diverse edge cases, and real-world artifacts. Our ultimate goal is to combine LMs with program analysis techniques to advance software engineering research. Thank you very much for your attention. I'm happy to take questions.
Okay, thank you. 老何 sorry 上来。Okay. Okay, there is no question and no question and answer. So if you have any question, you can contact the author by the email.